I know it's been an intense afternoon, a bit too much, too many slides, but okay, the last presentation is called Towards Sustainable Composites. It's saying that, yeah, we're not there yet. We have further to go. And I've only included some aspects, and you may always say, hey, I know about something else that should be here. Well, if you do, come and tell me, okay? And put it in for next year. Yeah, I did. The first slide always seems to have a problem with advancing. Okay, so we're going to look at these different things: policy, materials, applications, some manufacturing, 3D printing, and some unmet challenges. First thing I'd like you to do is to propose, how could composites help address climate change? Just quickly type in a few ideas. Big and small, operational, materials. Sorry, folks, I started pretty quickly because I'm running out of time. Didn't miss much so far. So lightweight mobility. Reducing CO2 emissions. Any last ideas? Oh, here they come. Longer lifetimes, yes. Yeah, I'm going to take another photograph of this one. Great, we're going to see a few more in this lecture as we go through. First thing I want to talk about is policy. When you leave here, there are some policies that you need to know about. One is the Green Deal. Anyone heard of the Green Deal in the EU? Two people nodding. Okay, the European Commission has set some proposals to try and reduce greenhouse gas emissions. And it set these targets. Some relate to renewable energy and some relate to transportation. So these targets are things that industry needs to work on to meet these Green Deal objectives. So in the European Union, they can't sell these disposable stirrers for coffee anymore. Okay, things are changing and it affects companies and what they're working on. And to prepare this lecture, I spoke to 5 polymer companies, interviewed them. Solvay, Dow, Radisi, a couple more, to see what they said. One thing that you need to know about is REACH, which is the registration, evaluation, authorization, and restriction of chemicals. This is European legislation. So some composite ingredients that we used to use are now banned under REACH because the chemicals were hazardous. Okay, so it's a legal framework, and you need to know about this thing called REACH that affects substances that are often used in composite processing. So just store that word in your head. I haven't got time to go in depth into it. But you get people in companies who spend their entire career looking at REACH compliance of a company's products. Okay. Another one is the end-of-life vehicle directive in the European Union, which basically says we need to reuse or recycle 85% of the car. So there is legislation at a European level that affects the end-of-life vehicle that we have to meet. Okay, so we're going to look at, first of all, materials from an end-of-life and recycling perspective, and then we'll look at bio-based materials. So from end-of-life and recycling, this is an upside-down pyramid where we want to try and prevent, reuse, repurpose, recycle, recover. Okay, so we want to keep parts for longer, design for dismantling. So that's the design part of the process. We want to reuse components, that can be maintenance and repair. We want to repurpose to keep parts going, often in a different application, kind of hard with composites. Then you come to recycling, which is where most people think about composites in terms of life cycle analysis and the different approaches, thermal, chemical, mechanical. You can do a range of processes here to recover materials, but the desirability is highest at the top. So not just recycling, but preventing. The automotive recycling approach today is you take your old Peugeot and you take out the fuel and you drain the oil from the shock absorbers. You remove the catalytic converter. You dismantle some nice to have parts like bumpers, big plastic components. And then you take it to the shredder and you crush it and you turn it into small particles of material. So that gets rid of about 80% of the vehicle. So unless you've dismantled your composite part, it's going to end up like this. So in the future, we need to dismantle more components from the vehicle. What you get is called automotive shredder residue. And there's a lot of this. We haven't got time to go into this slide in lots of detail, but it's a big pile of 2.5 million tons. And there's two fractions, what they call shredder fluff, which is all this bulky plastic stuff, the seating, and but it's also contaminated with hard to recycle materials. And then there's a heavier fraction. Car companies often make statements that this will be future treated using new technologies to a greater extent, but they haven't yet got it figured out. Okay, so be aware of this and be critical. Ways to recycle plastic from the end-of-life vehicle. Well, you can landfill, you can burn it to recover energy, you can use it to fire a cement kiln, you can use the feedstock in the blast furnace. Some different approaches. There are some better ones. These are the dominant polymers that are in this residue, but often it can be quite expensive to recover the materials. Landfill is becoming illegal in the European Union, so that's going out. So only 3 to 4% of plastics in cars are currently really recycled. So there's demand for the materials. In aerospace, there is no equivalent legislation to the end-of-life vehicle. So currently you've got 2,000 aircraft parked in the desert in the US or in other places, and a lot more military aircraft. And over the next 20 years, there'll be about 5,000 airliners to be withdrawn from service. Airbus had a project called Palmella looking at recycling, but the only commercialized method from this research for composites is to grind them up for use as filler materials in roads or in sheet molding compound. So you take your old Airbus that's got a carbon fiber tail. Today, that's what happens to it. And it's not good enough. We need to go further than that with recovering materials because they are very valuable. There's one company in the Netherlands where they buy old aircraft, they take them to pieces, and there's actually a database online where you can rebuy parts of the aircraft, service your Airbus. So they're starting to go that way, but there's no legislation for aerospace, end of life. I was very surprised. Glass fiber composites, well, if you look at wind energy, for example, what they do is they take the wind turbine, they chop it up into big chunks using mobile saws, like logging machinery, I suppose. Then they get this kind of regrind. And what they like to use it for is to replace hydrated or carbonated materials in Portland cement and as a fuel for the cement furnace. And they say that that can deliver 15% of the CO2 emissions needed, depending on how much of it you put in the cement industry. So to power the furnace and to help become part of the cement itself. But again, that's not really going far enough. You're losing so much value. We can also try and recycle by solvolysis, physical chemical separation. So you put your piece of composite with solvent, pressure and heat, and you get the fibers back. That is a way of recycling thermoset composites using solvolysis. So that's interesting. And there's a company here called Carbo NXT that were recently purchased. And they are here in terms of technology readiness level, TRL 8, and very attractive. So they now take old bicycle frames and bits of carbon mats and they put it on a conveyor belt and it goes into an oven without oxygen and they can get the carbon fiber back, okay? But it's all manual. You see in the video, people cutting out these things with scissors and hacksaws and putting it on a conveyor belt. So it's not as automated as those other factories that you saw at Airbus or BMW. So you run the risk actually that it costs more than the virgin material. But nevertheless, this company has converted waste into a variety of material feedstocks, either random fiber or chopped. They can't make a line fiber. You can't get back from woven product to a UD material, very difficult. But they've made a whole range of, well, their customers have made a whole range of products from recovered carbon fiber. So that is possible, okay? That is commercial. Chemical recovery of epoxy resins. There are two methods coming out. First is using dissociative chemistry, where we convert the resin into a thermoplastic epoxy. Evonik have a system now that's commercially available. So they actually break the cross-links. The second is associative chemistry. And this is a really trick material because below the TG, it's a thermoset, and above the TG, it's a thermoplastic. It's a vitremer, epoxy vitremer resin. So you can do wacky things. So you can heat it up above the TG and stamp form it, and then you can stick this and dissolve off the resin. So epoxy resins are really changing. People are reinventing them. Okay, I found that really quite fascinating. Using this thermoforming and solvolysis, you can get back to your carbon structure. Recycling thermoplastics is also possible using solvolysis, pyrolysis, or gasification. And this is like molecular recycling, as one of my industrial colleagues like to call it, rather than chemical recycling. So you basically break down the polymer into the building block to polymerize a new polymer. You're recreating the feedstock. And an example for polyamide is you take your waste carpet, your automotive parts, and you use here an ammonia reaction with the phosphate catalyst, and you get back to your adiponitrile, which is the building block of hexamethylene diamine, which is what you make polyamide 6,6 from. So you're not mechanically recycling, you're actually breaking it down into the molecular building block needed to remake a polymer. And when I spoke to the responsible for sustainability at Dow, he was saying this is the way to go. He was saying bio-based plastics, they don't like to talk about because of the conflict with water and agriculture and food. But here, there's a lot of waste plastic around that can be recovered and broken back down with really quite high yields. And if you run the chemical plant with renewable energy, the life cycle analysis is interesting. Something else which I just put in at the last minute that you'll hear about is blockchain technology. And it's basically a way to put a marker in the plastic material so that you can know what it is all the way through the value chain. So when it comes to reusing or end of life, you can know what kind of plastic it is, which company polymerized it, how many times it's been recycled. So it can pass through the recycling step. So it's a way of using secure cloud data to be able to track your polymer okay, through the stages of its life to help recycling. I hadn't heard of this word until 6 months ago. It's new to me, but it's a lot of people are talking about it. Dow and Solvay are both using this experimentally. Now to look at bio-based materials. Start with carbon fiber. You don't have to you can use different novel precursors and different carbonization approaches to reduce costs and improve your CO2 positioning. So this is a life cycle study of carbon fiber pultrusion using a conventional precursor and conventional carbonization. Here, someone's taken a bio-based precursor and they've used renewable energy for an efficient plant, and it completely changes the life cycle picture. So an example from SGL Carbon, they're trying to use, or they are using experimentally, algae biomass that they ferment to make algae oil. This is converted by hydrolysis into glycerine, which is then made to make the polyacrylonitrile, the PAN, which is the carbon fiber precursor. And then they convert the precursor into carbon fiber using kind of plasma and microwave techniques, powered by hydropower or renewable energy, wind energy, to make kind of a greener carbon fiber. And that's really interesting to me, because you could imagine that being scaled. It's not really competing with food. The problem is we need that in place. So if you want to make hydrogen storage tanks again, you need to have enough kiloton capacity in the supply base to make your tank. And this is like 20 years behind where we need it in society. But nevertheless, that's the kind of thing that's going on. People are looking at bio-based plastics. Here's an example from Evonik, where they're using the castor bean, where you can use that to polymerize nylons, a whole range of long-chain polyamides, PA610, PA1010, PA1012, to give very equivalent properties to their conventional petrochemical-based polymers. They can now polymerize this from bio-based material. The trouble is, I spoke to someone from Invista, which is a nylon producer, and they say it's biorenewable and it's great, but that land could be used to grow food. The water could be used to grow food. So it's very controversial. Technically, it's possible, but it has questions. Bio-based does not mean biodegradable, just to be clear. And biopolymers are not recycled polymers. They are polymerized from plants. There's also bio-based epoxy available. Solvay, a company we know quite well, has produced a bio-based epichlorohydrin base for epoxy. So that's now from vegetable glycol, derived from biodiesel, which comes from plant oil. So these resins are now becoming commercially available. Natural fibers, also very interesting. This is an EPFL spin-off, Decom. And they use European flax that they can weave, and then they can impregnate with thermoplastics. So you can see their value proposition. It's very good in safety, and they have some very interesting projects. Here I've got a nasty footnote. I don't know if this applies to them or not, but someone did a life cycle analysis on flax. And if you use fertilizers to grow your flax, phosphagen and nitrogen cycle, the environmental impact is really hit. If it's grown without those fertilizers, it's really better. So you have to scratch the surface and see what's below the paint, okay? If Decom are sourcing their flax that hasn't had high levels of fertilizer, it's really good. But if you're using lots of fertilizer, you're affecting that planetary boundary on the nitrogen and the phosphorus flows, okay? So you always have to think a little bit deeper to the global picture, not just, oh, it's a plant, because the plant didn't just grow in the field without some fertilizer, but maybe it did, I don't know. Question I need to ask them. A research project that's gone all the way from being bio-based, repairable, from self-healing, reprocessable, via the vitrimers, recyclable. You can read these yourself. Another one you may have heard of is self-healing composites, another EPFL spin-off, and this reduces maintenance. That's the hammer, it's the part. Reference composites, and this is the healable composite. By applying heat, they can actually heal fractures in the matrix, not damaged fibers, but fractures in the matrix. Okay, 12 years research in Veronique's lab has led to the startup, and it reduces maintenance costs and extends the lifetime of composites. A very circular approach. Okay, I'm going fast because we're running out of time. Applications, electric vehicles, a huge investment. This is investment in battery factories, in gigafactories. And it's just, we need to make sure that we have answered questions about the environmental impacts and the recycling of these rare earth metals and lithium, because you're all material scientists. So ask about these things. I'm going to have to go quick. Composites have a role to play in battery housings for vehicles, because you need to make these battery housings lightweight, and that's a key to their range and their increased adoption. So lots of people are looking at the battery case for electric vehicles. You can read about it here. Wind energy needs to become more circular. It's growing, like we said. There's a company, Siemens, that's now using a new resin, which is recyclable via solvolysis. So you can chop up your wind turbine blade, and rather than grinding it and putting it in the road, you can use solvolysis to separate the resin from the fiber and the glass, plastics and wood. Yeah, so you can really get back the materials with a higher value. Okay, if you're just grinding up the waste, it's got almost no value. Here you've retained value. This is a circular approach. So wind energy, chopping up, solvolysis, and that's very interesting and a way to think. Another important application is the hydrogen economy. And the idea there is that we can use hydrogen as a fuel source. It's got a high energy per mass, but low energy per volume. So hydrogen does give a very high energy density, and it is a key, the hydrogen economy, towards moving this curve down, especially when you're not using kind of dirty fuel to create the hydrogen, but you're starting to use renewable power. And hydrogen economy needs tanks to store the hydrogen in. So you can look at vehicles, you can look at refueling stations, boats, aircraft, trains, longer range vehicles, so not for in town, but for driving long distances. And they all need composite tanks to store the hydrogen in. So how can we make composite tanks circular in their design philosophy? Those of you who are doing the project will be aware of this. There are different classes of composite tank, and they use carbon overwrap in compressed gas and syro-compressed tanks. So we're going to need a lot of carbon fiber to help support the hydrogen economy. It's going to be a huge market area and a lot of work on pressure vessels. Airbus also have their zero-E concept. They want to have a zero-emission commercial aircraft by 2035. So they're going to fly aircraft around with giant hydrogen tanks rather than burning conventional fuel. Here you can see here a concept already for a 400-mile range Dash 8 turboprop aircraft where they slide in these tanks. You may say, well, hydrogen is highly explosive. Well, so is aircraft fuel. Who knows? That's just a trend, okay? Manufacturing. We talked about this diagram previously, and additive manufacturing is part of this. And I'm going to give you a super high-speed tour until the next lecturer comes in around additive manufacturing. The idea is that you can manufacture your product in different locations. Rather than having one massive factory, you can have dispersed factories. It reduces shipping. It's flexible and highly customizable with lots of design freedom, and the investment in a machine is much lower. Composite materials have been following additive concepts for a long time. You can see here thermoplastic toe placement. There are 4 companies doing this, where you take a tape and you heat and press. And now we start to see more and more of this going on. This is all kind of additive manufacturing kind of approach of thermoplastic composites. This is just chopped carbon fiber, but there are now large printers available that can print huge components. Really large boat hulls can even be 3D printed from different combinations of chopped carbon and thermoplastics. When we go on to look at continuous carbon fiber 3D printing, there are machines available which go from kind of desktop systems all the way up to advanced robotic systems. And I'm just going to quickly go through these as a quick tour. A company called Arrivo that can place bicycle frame type components by heating up tape and applying pressure with a consolidation roller. And it's basically advanced fiber placement, but renamed as 3D printing. Other companies 3D printing composite materials using a very simple industrial 6-axis robot. Another one, Aris Composites, where they basically use a robot to take pieces of tape, they ultrasonically weld the tape together into a preform, and they put that into a mold and press form it, and they can make really wacky structures that you couldn't make by any other method. 90 Labs, a Swiss company, they're placing strands of carbon fiber using a 3D printer, and then they put that into a second module and they heat it up and press it. So you can make a really complex kind of component by printing the fibers first and then heating it up. Mark IV's process, we have that one at EPFL, and here are some parts where this has continuous carbon fiber inside, printed on a printer. Another process, desktop metal, they can take a tape like this, carbon fiber tape, and they can print that, apply pressure with a micro AFP head. So like the big process you saw at Boeing and Airbus, but with a tiny roller, and you can then print a component like this thin, which has got continuous carbon fiber inside, and it's overprinted in short carbon fiber. Which, if it wasn't for COVID, I'd pass it around. So that's what you can see kind of coming out. Another company, an IsoPrint, which is the thermoset process. That's got carbon fiber printed inside it. So we're starting to see composites moved in this direction. A thermoset system using UV cure of resins, and they can print some really interesting structures. Okay, we're not going to have time to go through all these things. Looking at some properties, some normal weight specific yield strength, we can get some amazing properties with these 3D printed materials because they're highly directional. You can put the fibers really where you need them. That's the interesting part. And I'm going to play this video because it's kind of cool. This shows the combination of toolless 3D printing, where they print the mandrel and then they print onto the mandrel. So they start from nothing, turn on the lights, very dramatic. Okay, it's a robot, nothing here, and they print their own tool and make the composite parts, all from additive manufacturing. So that's the continuous carbon fiber, and this is the plain polymer, this is the tape. So they're now printing their own, 3D printing their own man. Switch to the plastic placement. So you get the idea. Very cool process. So that's all been done without a molding tool. You can have that robot in different locations and make the same part without having to have a big factory. Okay. And you can start to see here, people are overprinting honeycombs onto a laminate, and they're combining filament winding with printing their own mandrel system and the attachment points to go inside the tube. So it's starting to revolutionize composite manufacturing. That's what I would like to say. People are starting to mix metals and composites. They're starting to embed conductive fibers inside the composites. So you're looking at multi-material systems, stiff and flexible, damping, conductive. So your design freedom is going up and up and up if you can start to put conductors in your composite as it's printed. Because we're going to run out of time, I'm just going to skip to the last slide. What are the unmet challenges? This is from a company, consulting company, relating to the widespread adoption of circularity in composites. There are technical challenges relating to the limitations of materials. Some of the parts, like wind turbine blades, it's the different sources, trying to sort out the different materials. So sorting is complicated. That's where blockchain can help. Market looks at the value chain, and we need to make sure that the secondary materials are cost effective compared to the virgin product prices. And then the policy in Europe is not really in place yet to enable composite circularity, but that's something that will come, I believe. So, one last Slido. How interesting or relevant do you think is incorporating sustainability themes into lectures? So 5 is good and 1 is bad. Okay, so 11 of you have responded. It's a small statistical sample, but if you have any suggestions afterwards, feel free to come and talk to me how it can be improved next year. You know, it's the first time, so it can always be done better. I'd like to thank you for your attention and listening to me talk away for 3 hours in English. I really appreciate that. So thank you.
Thank you.